Okay, so today I'm going to first of all prove Neumann's lemma. Definitely, I'm going to do that, and I'll try to get as close as possible to Transseries, and we'll see precisely how far we can get. But I don't want to rush it through just to get there. So let's see. Let me make as usual a bit of a summary of what is the situation so far. We mentioned, we explained what Hahn fields were. So Hahn fields are sets of formal sums of coefficients in the real numbers. In this case, we're just working with the real numbers, and multiplied by monomials. And the monomials are in some given abelian order, the abelian group. Okay, and the sum makes sense when the support of the sum is anti-well ordered, which means that the set of monomials where the coefficients are non-zero is anti-well ordered, so it has a maximum, and then every non-empty subset has a maximum. In this way, and this codifies the fact that the sum is a sum of smaller and smaller terms as you go along, and the tail is always smaller than anything that came previously. Okay, the technical thing that we have to keep in mind is this notion of summability. So whenever you take a family of series in a Hahn field indexed by some set, you say that it is summable when the union of the supports is also anti-well ordered, and each monomial appears at most finitely many times among this series. So which means that the set of indices such that the monomial appears in the support of Fi is a finite set. Okay, because in this way we can define the sum of the entire family, and we just say for each monomial we attach the coefficient, which is the sum of the coefficients of the same monomial in the various elements of the family. By condition 2, this is a finite set, so we can do the sum. We are free to do that, and then the entire sum is another series in the Hahn field because the supports are anti-well ordered. The union of the supports is anti-well ordered, so you're sure that this is going to be a sum of the same shape. So this is sort of the technical thing to have in mind. The other things we've seen, I'm not going to repeat them again. Well, I'm going to say them very quickly. We've seen the Surreal numbers have this convoy normal form, so they can be written as these infinite sums indexed by ordinals of, again, monomials multiplied by real numbers. Monomials now in the sense of this group omega in the surreals. And we have this identification. The surreals, you can see them as almost a Hahn field, rather a union of Hahn fields. So this is the union of all these Hahn fields of form Rm, and the group of monomials is ranges over all the subgroups of these omega, which are sets. And the formal thing that we do is that every time you take a serial number, you write its convoy normal form, and you can identify this with an element of some Hahn field just by taking this formal sum, and you think of it as the sum of a summable family in the Hahn field. Okay, and you can always stick a group here, which is a set, because the support of this sum is indexed by an ordinal. So the set of the quantity of monomials that you need to do this sum is always small. You can take these monomials inside some set. You take the group generated, is still going to be a set, and then you can use that to make a Hahn field around it, and you can do this identification. Okay, so the thing we have to do today now is to prove this lemma. Okay, now this is the crucial thing for today, which is whenever you take a series in a Hahn field where all the monomials are less than 1, or in other words, when this is infinitesimal, and then you can take any real coefficients as you want, and then you take the family of the powers, the powers of this epsilon, powers in the natural numbers, multiplied by these coefficients. Well, this is a summable family, always. Okay, now I'm doing this when technically I wrote this in the general version where you have, so this epsilon is actually a tuple of infinitesimal series, but for simplicity, think about a single series, and then you take all its powers, and you're writing a power series now in the series epsilon with real coefficients. And the claim is that this is summable, and the application is that then you can define analytic functions on your Hahn field just by using Taylor series, and you know that this is going to be by the summability you can make sense of this infinite sum here. Okay, and then there's global exponentiation, but we're going to come back to this later. First, we should do this Neumann lemma. So let's see if I can give you a solid proof in a single page. Okay, oh, too much. All right. Okay, so Neumos Lemma, so I repeat again, the statement is this one. We're just going to do L equal 1. So what we want to do is we take an epsilon infinitesimal, and we want to say that the family of the integer powers of epsilon, the positive integer powers, is summable. Okay, so we start with the general comment first, the general definition. So to clarify this summability, how do we see that? How do we measure that? Take some family in your Hahn field. It could also be the surreal numbers, as long as you index the family by a set. So it will be, and then it's just a special case. Okay, and then look at the sequence like this. This is a sequence indexed by natural numbers, and the sequence lives in the set of indices, the Cartesian product of the set of indices and the set of monomials. Okay, so you're sending n to one index in in the set I, and to a monomial in M. Okay, and well, which sequences are we considering here? So we call this sequence bad. Well, bad for this particular family when we have two conditions. One is that the map sending n to In is injective. Okay, so you want this I to In to move across the indices and never go back to the same one. And the sequence Mn is weakly increasing. Okay. Okay, why am I calling out this sequence bad? Well, because we have this observation.
But Vincenzo,
yes,
don't you want to say that Mn belongs to the support of something?
Oh, I was forgetting an important piece of information. Yes, I thought I had too much space and I could just write large, and it was suspicious. So the sequence Mn is weakly increasing, and Mn in the support is in the support of Fin. Okay, yeah. Otherwise it doesn't say anything. Okay, so what's this doing? I mean, you're picking out elements Fi, a sequence of elements Fin among this family injectively, so you never go back to the same one. And then every time you take a monomial in the support of Fin. Okay, and what happens if this is weakly increasing? What happens is there's going to be a problem with the family in the sense that either, for example, one monomial is appearing infinitely many times across the family, Or you can, for example, or maybe you can find a strictly increasing sequence. And that means that when you look at the supports here, or the FIs, the union is not going to be anti-monoidal. You're going to find an increasing sequence of monomials in the union. So easy exercise. I told you more or less that what the pieces are. The family FI is summable if and only if there are no bad sequences. Okay. Okay. So now we want to do the same for we want to apply this. We want to use this particular test to check that that the family of powers of epsilon is summable. Okay. So now let's say let's pick epsilon in Rm such that epsilon is infinitesimal, and pick some real numbers R. Okay, I don't want to use N, checking on the Ri in R. And we want to prove that Ri epsilon to the I is summable. Equivalently, we want to show that there are no bad sequences in this particular family. Powers of epsilon times possibly a real number. Okay, how do we do this? Well, there's a nice thing we can do with bad sequences. So there is a partial order. We can say that the sequence IN MN is strictly less than JN ON when, and essentially we're going to do a lexicographic ordering, essentially because the orders are moving all over the place. So you look at the first N where the two sequences differ, the first N where they differ, we have what? You have that IN is less than JN, or IN is equal to JN, and MN is greater than ON. Okay, so you go along the sequence, and as soon as you see a difference, you compare the index. The index is moving over the natural numbers because this is the family of powers of epsilon, positive powers. So the index is the exponent, and you compare that. And then if the exponent is the same, then you want the first monomial to be greater than the second monomial. I apologize for this asymmetry between the two. One is one way, one is the other, but that's what we need. Okay, so we have this order among sequences. Well, among backed sequences, that's the only ones. These are the only ones I care about. And now my claim is that there is a minimal. Sorry. This is a proof by contradiction. So if there is a minimal, if there is a bad sequence, there is a minimal one. Minimal according to this order. How? So why? Well, you can just construct it. So you suppose that there is some bad sequence. Okay. Then among all the bad sequences, you can choose the ones where I naught is minimal. Okay, is the minimum possible integer natural number appearing at the beginning of a sequence. So we can just pick y naught minimal. And now you say among all the sequences, bad sequences, having I naught as the first component of the first element of the sequence, you choose the ones where the monomial is maximal. M naught is maximum. Why can I do that? Because now once you fix I naught, then the monomial M naught is in the support of epsilon to I naught. So it's in the support of a fixed series, and the support is anti-well ordered. So among all the possible monomials in this support, we can choose the maximum one that appears among bad sequences. And so I can just do, I pick Y naught, then I pick M naught maximal, and I continue. So now I fix Y naught, M naught. I look at all the possible bad sequences with this first element. I look at the second one, and now I choose I1 minimal. I1 minimal. And I keep doing this. Just alternate. And what happens, the end result is a bad sequence. Okay, why? Because the indices IN are injective, because by construction, each one is, each finite piece of a, let me put it in this way, each finite piece of the sequence, as I built it, is part of a larger bed sequence. Because by construction, we're taking Y naught minimal at the start of a bed sequence, then we fix it, and M naught is maximal, such that there is a bed sequence doing that. And so we know that no IN can be repeated, because by definition of these bed sequences, this map is always injective. So it remains injective as we do this construction. And likewise, the monomials that are appearing M naught, M1, they're also going to be weakly increasing because of this. Okay, so this is going to be a bed sequence as well. And by construction, it's minimum, because we're taking everything minimal, alternative, well, it alternates between minimal and maximal, so that with respect to this order here, the end result is a minimal sequence. Okay, and this is really the core of the argument. Okay, the fact that there is a way of building this minimal bed sequence. Okay, now I claim that given a bed sequence, I can always generate a smaller one. Okay, and that's clearly in contradiction with this claim, because we said we're taking a minimal bound. So let's pick this minimal sequence, and let's do the next step. Now we go deep. Now we actually use that the sequence is made of the powers of epsilon. So right, we look now at these monomials, Mn. Mn is going to be what? Mn is in the support of epsilon to the In. So it's going to be some product of monomials I and 1 all the way to O of N In, where these monomials O and j are in epsilon to the in the support of epsilon to the in. No, oh my. Mn is in the support of epsilon to the in, so I can write it as a product of monomials in the support of epsilon. Okay. And now it's crucial that now this epsilon is always the same for everybody. Okay, it's just this one, and it's infinitesimal. Okay, because now what we know is that the support of epsilon is anti-well ordered, and we know that everything is less than 1. Everything is infinitesimal in epsilon. So let's use this information now. Let me do an easy case. So suppose first that now we just look at the sequences of just the sequence ON1. So just the first monomial in this product. And suppose that this is decreasing, strictly decreasing. Okay, it's not going to be in general, right? But just to see what's going on, then what I can do is, well, then divide it out. So I divide each mn by the first monomial. So essentially I just delete it. So the thing we should sort of imagine is that we just moving this guy here. And what I obtain is another bed sequence, a bed sequence where the indices all go down by 1. Because now, after I divide by O and 1, every monomial is going to be in the support of epsilon to the in minus 1. Okay. But if I can do this, then I'm contradicting the minimality of the sequence I started with. And basically, in this very special case, I just have that this trivial observation I naught minus 1 is less than I naught. But I still so I find a smaller sequence, but the sequence is still bad because and now there's a bit of contortion. If I divide everything by a decreasing sequence, then everything is moved up in such a way that if I start with a weakly increasing sequence, the end result is a strictly increasing sequence. Okay, because so I'm dividing everything by something always smaller, so everything gets moved up more and more as you go along. Okay, and you're still bad. So you remain bad because if you're starting bad sequence, we were starting with a bad sequence, it becomes strictly increasing, which is even worse actually in a sense, and so it's still bad. And that's a contradiction because we just said, well, we can pick a minimal one, and now we constructed a smaller one. Okay. Now, given this, okay, this is the special case. If you do have a strictly decreasing, if these monomials are strictly decreasing already as given, then we're done. If not, well, now we have to do something more sophisticated, and this is the part that needs to be said carefully as well, because what happens is these monomials are in the support of epsilon. The support of epsilon is anti-well ordered, and that means there's going to be a subsequence of these monomials, which is weakly decreasing. Okay, in general, there is a subset of n on which the sequence ON1 is weakly decreasing. Okay, that would be a subsequence. And now I would like to do the same now. The same procedure. I would like to divide the monomials of these monomials Mn by these guys. I can only do this on a subsequence. But if I just, if I just go to the subsequence, then the initial index of the sequence might change in an unpredictable way. And so I don't get something minimal again. So I need to be slightly smarter about this. So we take the old sequence on the indices before the set A. Okay, so I keep going along the sequence until I hit the special subsequence. And after that, I divide by these monomials and I stay on the subsequence. Then continue continue on A and divide by ON1. Divide each term by the initial monomial. So you still do this cancel, you cancel out that the first term, but only from that point onward. And from that point onward, you only stay on the subsequence. You forget about the rest. And let's see if I can write something legible. So the thing you're going to get in the end is something like I0, M0, and there's going to be some K where K, say that K is the minimum of A. So I go all the way up to IK minus 1, MK minus 1. And then here, I start the subsequence. I'm going to have IK minus 1, MK divided by OK1. And then the next one is going to be some IK1, the next number in A, and minus 1 as well. Minus 1. And here I have MK1 divided by OK1, 1. And I'm afraid that you can't see, I can't see now the smaller subscript myself because I'm stuck in too many of them. But it should be, I hope it's readable just enough to see what's going on. So I follow the old sequence up to the beginning of the subsequence over the set A, and then here I divide, and by dividing, I also decrease this index here. Now, this sequence is still bad, except for one case. I don't know if anybody's going to notice, so it's going to be an exercise is to fill out the details of this proof, fill the remaining details. But this sequence is still bad because the monomials were weakly increasing. From some point onward, we divide by a weakly decreasing sequence. And now finally, we use the fact that epsilon is infinitesimal. And we also divide by things which are smaller than 1. So, and this is important because now I need this because I need to know that I started with this MK minus 1 smaller than or equal to MK. And since I'm dividing by something smaller than 1, oops, this gets bigger. So it remains bigger than mk minus 1. So this is where I use that epsilon is infinitesimal in this very final step. Okay, and now since the OK, these monomials O at the denominator are weakly decreasing, the sequence remains weakly increasing. Okay, and I'm contradicting now the minimality because this index went down by 1. Okay, so this proves, and again, this is a contradiction because we said we can take a minimal sequence and we constructed a new bed sequence, which is strictly smaller according to this order. Okay, and that's one proof of Neumos Lemma. Okay, I think so that's the
Vincenzo. Yes. So what you proved actually is that you write small enough, the proof of Neumann's lemma needs only 1 page. Is that?
Yes. Yeah. I mean, can you read? Oh my! On my screen, it's readable. I hope that Zoom is not compressing this too much. Yes. Any questions? I mean, if something is not readable, ask me now, and I'll try to improve it. Okay.
Oh, yeah, this is looking a little small for me.
Okay. So I won't do this again. Next pages are going to be better. Can you see the final line with the new sequence?
Excuse me, I just have a question.
Mm-hmm. Yes.
When you decrease this ik to ik minus 1,
yes,
can you still guarantee that you have an injective sequence?
Aha. Excellent question. Yes, that was the small gap I was leaving in the proof. A posteriori, yes. Okay, because what happens? The sequence of the INs by construction is strictly increasing because I noticed the minimal one at the beginning of a bed sequence. So all the next indices are going to be greater. Otherwise, you could just take another one. Okay, so the INs are increasing. When you drop and you do this -1, the only thing that might happen is that it collapses on the previous one. So the worst thing that can happen is that these two indices become equal. Okay, and now what you know is that mk minus 1, it was less than or equal to mk. You divide by an infinitesimal, then mk minus 1 is strictly less than mk. Right? So in this special case in which the two things are equal, well, I mean, this always happens. This guy is strictly less than the next one at this particular stage. But now what does it mean is that now I'm going to use another color again. In this case, what I do is I drop this one. Okay, because what happens in this order between sequences, I don't only take the minimal index, I also take the maximal monomial. Okay, so in this case, what happens is that instead of changing the index stays the same, but I increase the monomial. Okay, but there is one thing I need to do, which is actually to raise one term in this special case. It's the thing I was not saying. I was cheating. Yeah. Is that convincing enough?
Yeah, okay.
Okay, yes. So again, so that's why you need to be careful. You really need to take the sequence minimal in with the right partial order here to make this everything work in properly. And that's why yesterday in the Q&A we were saying this proof is a bit fragile. if you don't really put all the pieces in the right place, at the end, you have these small gaps that might appear. But it doesn't happen because of this reason.
Could you say a word about the multivariate case?
The multivariate case is essentially the same, but instead of having, when you take, but the difference is now the indices are vectors of natural numbers. Okay, and I think if you just put any total order on these tuples of natural numbers, then you should be fine. That's the biggest change. Let me think. I haven't actually thought about this proof in the several variable case. I mean, this style of proof. But that's the only difference. I mean, what matters is that you have a meaningful way of well ordering this set of indices. And yeah, I think what I would choose, for example, is I would just take, I order the exponents first by the sum of all the exponents, so by the total degree of this power that you're doing of epsilon, and then lexicographically by the single component. That's one option. And then you do the same argument by minimality, minimal index, and then maximal monomial.
Okay.
Other questions? Okay. Once again, this is typed out in Beamer, so we're going to upload slides with these things typed out and not with my bad handwriting. So that's going to be a better reference that you can use to review this if something doesn't add up after the lecture. Okay, so the main corollary of this lemma is that you can define an analytic function. So whenever you have a real analytic function on an open subset of the real numbers, you can extend it to the same open set plus all the infinitesimals. Okay, because the point is, at every point in the open set, by definition, there is a Taylor series for the function. And then if you move around by an infinitesimal, you use the Taylor series. And that's what was written here. This extension is just given by, you compute the function and its derivatives in the real number, and then you use the Taylor series in epsilon to find the value. And this is summable by this lemma. And so you can do this. Okay. Okay. So at this stage, I'm going to now take away the proof of Neumann's lemma. And actually, I forgot to do a trick. Yeah, but I'm trying too many new things. If you open this link, you should be able to see the same, everything that I've written up so far. In case you want to go back right now. Okay. So
I'm afraid your link doesn't work.
it doesn't.
No, I'm afraid so.
Yeah. I've tried. It works on my computer.
Okay.
Oh, it requires a password or something.
Okay.
Approval
Yeah.
from Vincenzo, probably.
Well, my bad. Okay, I should test this more carefully. Oh, I see. Oh my, I really thought it was. Give me just a second. Oh yeah, I'm receiving requests for authorization, so I'm going to very quickly try to fix this problem, because there should be a link where everybody can access. Clearly, I gave you the wrong one. Okay, this other link should work. Fingers crossed.
It works. Yeah.
Okay, great. Okay, so now moving on from this, we have finally this. Okay, so we have a proof that you can do this Taylor series, at least in the case in one variable, and in general cases, maybe exercise again, if we need to give some work to the students. So we can apply this, and the main theorem we do have to remember is that now, if you take all the restricted analytic functions on surreals, by restricted I mean you take an analytic function, I mean any function on some open set containing -1, 1 to the L for some natural number L, analytic, and then you take the restriction to the box -1, 1 to the L, to the compact box. Okay, so you add all the functions, these functions to your language. You also add the global exponentiation. You do the same on the surreals using this way of extending analytic functions by using the Taylor series and summability, and you get an elementary extension. Okay, so you get a structure that satisfies the same first order formulas. Okay, so let's make this now. I don't know if everyone in the audience, either now or for the recording, is completely familiar with elementary embedding. So let's make one concrete example, in any case which leads up to the topics, to the next step, which is we start with the classical definition. So a log x function or logarithmic exponential function is a composition of exp, log, and algebraic functions. Okay, algebraic functions in several variables, which just means basically you can invert polynomials and stuff like that, and you can. I don't want to go into that. For example, square root. Okay, square root or things like that. The key thing is that the germs. Now, if you look at this, the germs at infinity of these functions, because they're all defined on this germs. For L equals 1 are totally ordered by this order that Lau introduced in his first lecture, I think, is eventual less than. So you say, if you say that the function is less than another, if eventually the values of one are less than the values of the other, so f(x) is less than g of x from some point onward, then this is a total order on these particular functions. Okay, it's non-trivial, right? I mean, this is not this is not obvious. Okay, now in this case, since we have all the machinery of minimality, there is a trivial reason. The trivial reason for a model theorist is these functions are obviously definable in Rexp, and we know that Rexp is minimal. So that's it. If you compare f of x and g of x, eventually one must dominate the other, or they must coincide. There's no other option. Okay, but now the thing is, in this particular case, what I want to say now is that we can use now everything we said so far to extend these functions to surreal numbers. Okay, so there are canonical, well, let's say natural, and then we can debate whether natural is the right word for this. Extensions and A to the n N O serial numbers of all log x functions. Okay, how do I do this? As I was saying, the trick is in this case, each log x function is defined by some formula in the language. Well, let me say an exp, just because it's the only language on this slide that is actually written explicitly. But actually, you don't even need analytic functions. You can actually define it only with this part of the language, okay, lexp only. Okay, and now, what does it mean for a formula to define a set? This means that the graph of the function is a definable set, which means the graph of the points on the graph are precisely the points satisfying some formula. Okay, and now this is how you define the function f over the reals, and now you use the same formula on the surreals. And since this is an elementary extension, the fact that the point satisfying a formula formed the graph of a function remains true, because it's a property you can write with another formula. So you do that, use it, use the same formula, use the formula in this larger structure. It defines a function because it's an elementary extension. And for example, by similar arguments, the end result doesn't depend on which formula you use, because if two formulas define the same function, you can test this with another formula, and that other formula remains true, and it keeps telling you these two formulas define the same function. So this is well defined. So this extension is well defined, and it gives you a way of extending the functions, and it's going to preserve all the first order properties, because it's just an elementary extension. Okay, and so exercise, for example, is that the map sending the germ of a function f to its value, is injective and order preserving. Okay, so you take a germ, not the function itself, but just a germ. This function is going to extend to beyond the real line, you take the value in omega. This map is injective, so if two germs are different, then the value in omega is going to be different. Okay, and now what's nice here is that the exponential normal form of this FNO omega is essentially an asymptotic expansion of F. Okay, and so I'm going to conclude with the same example that Alessandro spelled out in the last lecture with other calculations. And the example is this one. Take this function.
Sorry, Vincenzo, F is a log x function or a definable function? What is it, F?
Oh, okay. Sorry. I mean, at this stage, I only wanted to say log x function. But what Alessandro said is also fine. Every definable function in R and X.
No. The reason I ask is that if it's a log x function, then the germ should determine the function itself, right?
Yes.
So germ of function
no.
is the same, or no?
Oh, no, sorry, no. I mean, a function is an actual function from some interval on the reals.
Right.
But this map is injective only at the level of germs.
Okay.
So if two functions coincide from some point onwards, then this from some point onwards is going to extend to an interval containing omega.
Okay.
Yeah. So this is only at the level of germs. Yeah. Yes, and also this statement also works for germs of definable functions. I mean, if you can prove this using everything I've written, just what I've written here, actually you can extend it to all definable functions in Rn. So it's not a deep statement. It's more of an observation. Okay, and the example, and then I should stop because I'm over time, would be something like this one. I take the function x1, x plus 1 to the x. This is a log x function because I can write it as e to x log x plus 1. Okay, x plus 1 is algebraic. Then I apply log, I multiply for x, and multiplication of two functions is an algebraic function in two variables, and then I take the exponential. So it's a log x function. And if I map it to the surreals, I get omega 1 plus x. And last time on Monday, Alessandro showed that he made an explicit computation. You get e to the e times omega to the omega plus, minus e over 2 omega to omega minus 1 plus something else. And actually, if you look at this other function, then the expansion is going to be just the same, the x in place of omega. Okay, so the Surreal numbers are just doing these formal expansions. When you go to infinity, they work in this way. You can think of them. You should think of them now as infinite sums, as just as generalized power series. And the way you apply analytic functions and exponential and log is it works in the formal way, the same way you would use it on formal series. Okay, I stop here. And yeah, Transseries will come in the next lecture then.
Thank you.
Thank you.